Thanks for joining me. We're about to go through and do some practice problems. Now, you know we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin.
Sketch the domain of the function f of xy, square root 1 plus xy, log 16 minus x squared minus y squared, downstairs another square root, 4 minus x minus y. All right, now, when we talk about sketching of the domain, basically we're saying, let's figure out our three issues. Okay, so what are our three issues? And in other words, what do we want to avoid? Well, we want to make sure that we take a square root of things which are greater than or equal to 0. We want to make sure that we have a log of things which are greater than 0 and no divide by 0, right? So those are our three things. So as we're making our decisions, we say, okay, let's go through and say, how does this affect things? All right, so there's really three pieces here, so let's just go through them one by one. So let's start with the square root of 1 plus xy. It's upstairs, so that's good. Don't need to worry about any divide by 0. It is a square root. So I say, the square root of 1 plus xy, that tells us we need 1 plus xy to be greater than or equal to 0. All right, well, now, this is not always so clear what that is. So let me just say, let's do equality. So if we do an equality, xy plus 1 equals 0, xy equals minus 1, or y equals minus 1 over x. So we'll sketch here. Okay, so 1 over x would be that part, minus 1 over x flips it. So we have that. All right, now what do we need to be true? We need to have 1 plus xy be greater than or equal to 0. And I want to figure out which of these regions are going to be included. And I drew it with a solid line because I do have an equality there. Well, when in doubt, test points. 0, 0. Does 1 plus 0 times 0 give us something greater than or equal to 0? Yes. All right, well that says that point's in there. But wait, if that point's in there, everything up to and including the boundaries will be in there as well. All right, so we have that. And now we say, okay, what about other points? Well, say I pick a point out here where x is negative 2, y is positive 2. 1 plus negative 2 times positive 2, that's 1 minus 4. No, that's not greater than or equal to 0. So that part is out. It's not in our domain. All right. How about point over here? X is positive 2, y is negative 2. Same thing. It's going to get a negative value out. All right. So just from this part, we must satisfy that type of setup. All right. That's one issue. Now let's talk about log. All right, so we have log 16 minus x squared minus y squared. Say, okay, that part needs to be greater than 0. So 16 minus x squared minus y squared has to be greater than 0, or x squared plus y squared has to be less than 16. All right, now, what's that? That we can probably recognize. That's a circle. And that's a circle of radius 4. And we're not going to include the boundary because it's dotted. Now, are we on the inside or the outside? Well, when in doubt, pick a point. 0, 0. Does 0 work? Yeah. 0 squared plus 0 squared is indeed less than 16. So we include the inside of that. All right. By the way, these are not quite the same scale. We'll get a better picture when we put it all together. And now, this last part, square root of 4 minus x minus y. Now, it's a square root, so we need the inside to be greater than or equal to 0. But, see how it's downstairs. Because it's downstairs, we also can't have it be 0. So, we have this last part, the square root, 4 minus x minus y. That tells us that 4 minus x minus y must be strictly positive. Or, you can say, oh, that says x plus y needs to be less than 4. And if you sketch, well, where are some points? If you put in x equals 4, y equals 0, or y equals 4, x equals 0, those are 2 points, and then this will be a line. Now, which side of the line are we on? Well, pick a point. 0, 0. Yeah, 0 plus 0 is less than 4, so we're on that side of the line. All right, so now what is the final answer? We have to put all of these together. All right, so let's do that. Okay, so remember, we just have to sketch. And usually they'll give us something with a grid, so it makes it easier for us to work with. So I'm going to mark some numbers here, 4, and negative 4, positive 4, negative 4. There is the circle. We have to be inside the circle. But we also have to be below that line. So I'll go ahead and include some additional details. And now we also have these curves. Now, note, if we plug in negative 1, you get positive 1. So it actually passes fairly close. So we're going to get here and here. All right, so we are now ready. We have the following. We're going to put a circle here because we can't include that. And then we have dotted lines. And now we shade where they all overlap. And we get the following picture. Very dramatic pause, right? But all right, there we go. So it's part of a circle here, straight line here, these curves y equals 1 over x, solid line here, everything else is dotted. And there we go. We've channeled our inner artiste, right? We can draw pictures. Yeah, mathematicians are allowed to draw. Why not? Sketch and label the level curves for the function f of xy is y plus 1 minus x squared over y squared plus 1 for the values or heights of 0 and 1. So heights here, think of it like topographical map. All right, so what does this mean? Well, that says 0 and 1. These are z values. So for z equals 0, we're going to set our function y plus 1 minus x squared over y squared plus 1 equal to this value 0, and then figure out what the curve looks like. Well, that's y plus 1 minus x squared equals 0, or that's y equals x squared minus 1. So that's a parabola. Okay, so we'll sketch that parabola in a second. For z equals 1, we'll have y plus 1 minus x squared over y squared plus 1 equals 1. All right, that's y plus 1 minus x squared equals y squared plus 1, right? Just multiply across. And then say, well, we can cancel off some 1s. Let's move everything to one side. This is x squared plus y squared minus y equals 0. And it's feeling very circle because you see x squared and y squared. And it's feeling very circle because it is a circle. Well, all right. So we want to complete the square. Negative 1 divided by 2, negative 1/4, square it, add 1/4, 1/4. So this is x squared plus y minus 1/2 squared equals 1/2 squared. Okay, so that's a circle. It's a circle of radius 1/2 that's been shifted up so that the center is at 0, 1/2. All right, so now we've done the curves, we have to do the sketch. So what does this look like? Well, we can get a pretty good drawing here. This is good enough. X squared minus 1, it's parabola, but moved down by 1. So we'll mark some points here. And we have our parabola. And then this is a circle of radius 1/2 shifted up. So it turns out that as far down as this goes, we're going to go up that amount, and we have a circle. So those are our two level curves. Now, that's the drawing. We also have to label. So we have to label, so we say, well, the parabola is 0, the circle is 1. There we go. So you're drawing two curves, and life is good. Nice. Woohoo. All right. Find the derivative of the function f of xyz equals x squared y plus xz squared minus 4yz at the point P, 1, 2, 1, in the direction of the vector v, 6, minus 3, minus 6. All right. What kind of problem do we have? Well, there's two key words that pop out to us. Derivative, of course, we're always on the lookout for that because it's calculus, come on. Direction. This is a directional derivative. Okay, so now we're trying to take the derivative in the direction, in this case, of the vector v of the function f at the point P. The formula that we need to remember, this is the gradient of the function at P dot V. Now, we have to be careful here. When we say V, is that V? No. Yes, it says V, but it's not the V we need. Okay. Remember, we're going to have to work with a unit vector. So, we've got two things. We've got to make this into a unit vector. We've got to find that. So we have to do them both. It doesn't matter what order we do it in. Let's go ahead and get some low-hanging fruit out of the way. Let's make this into a unit vector. Now, I can start by saying, let me scale, and I don't want to flip the direction. So when I scale, I don't want to scale by a negative value, but if I can scale by a positive value, same direction. So since everything has a factor of 3, for simplicity, let's divide out by a factor of 3. 2 minus 1 minus 2. All right. Now, find the magnitude of that. That's the square root of 4 plus 1 plus 4, square root of 9, and that's 3. So, our vector is 1/3, 2 minus 1 minus 2. Okay, this is our unit vector. Now, if you didn't scale by 3 initially, you still would get the same thing. But then you have to deal with the square root of 36 plus 9 plus 36. Not that hard, but I just like to make life easier on myself because I care about myself, and you should care about yourself. Make life easy. All right, now that was fun. Put that off to the side. We'll come back and use it later. Gradient of f. So let's start by finding the generic gradient. Now remember, the gradient is your collection of partial derivatives. So f sub x, f sub y, f sub z. So for us, I'm going to take f sub x, taking the derivative with respect to x. All of the y's and z's are constant at this stage. 2xy, z squared, 0, comma. Take derivative with respect to y. X squared, 0, minus 4z. Take derivative with respect to z. 0, 2xz, minus 4y. All right, so there's our gradient. Now, plug in the point. So gradient of f at 1, 2, 1. Well, what does that say? Everywhere where you see an x, put a 1. See y, put a 2. Or see z, put a 1. So 2 times 1 times 2 plus 1 squared, comma, 1 squared minus 4 times 1, comma, 2 times 1 times 1 minus 4 times 2. Well, okay, that's 4 plus 1, also known as 5. This is 1 subtract 4, also known as negative 3. And this is 2 subtract 8, which is negative 6. So 5, negative 3, negative 6. All right, so now we found v, we found the gradient. We're almost there. Last thing to do, plug it in and get our answer. So we are going to take 5 minus 3 minus 6 dot 1/3 2 minus 1 minus 2. Well, the 1/3, I can just put that into the front and work the dot product. 5 times 2, 10. Minus 3 times minus 1, 3, positive. Minus 6 times minus 2, 12, positive. All right. And so what do we end up with? 10 plus 3 plus 12 is 25. So we end up with 25 over 3. And there we go. Nice. Woo! They love directional derivatives. And so just remember, find your gradient at your point. Find your unit vector. Life is good. I bet you we'll see one again. Find all the second partial derivatives of the function fxy equals log 1 minus cosine xy. Simplify as much as possible. Okay, we're in for a ride. Now, second derivatives. What are we going to have? Well, first you have to start with the first derivatives, and there's going to be 2 of them. One for x, one for y. And then for second order, there's technically 4 of them, but 2 of them we can put together. So namely, there's xx twice with respect to x, yy twice with respect to y, and then there's what we call the mixed ones, xy, yx. But for nice functions, basically anything you can write down, they'll be the same. All right, well, so we're going to take lots of derivatives. We'll need a lot of space. Let's pace ourselves. We're in for a treat. So we start with our first derivatives, right? You can't take a second derivative till you have a first derivative. So we have logs. Now, when you're taking the derivative with logs, very simple. It's a fraction. What's inside goes downstairs. And then you take the derivative of the inside, that goes upstairs. Derivative of 1 goes away. Derivative of cosine, negative sign, it's already negative, so it becomes positive sign. And then you have xy times the derivative of the inside with respect to x would leave you with a y. All right, similar, fy. Well, again, fraction, downstairs. And now, derivative of the inside, well, 0, derivative of cosine negative sign, so it's positive sign. xy times derivative of the inside with respect to y, which is x. All right. First order derivatives Done. Now to the second order derivatives. Now things are going to get more interesting because it's not just a log, it's quotient. What do you need? Quotient rule. Okay, so we get through this 3 times. Now, before we get too far, I'm going to make a comment here. There's a check that we can do a little bit of. Namely, do you see here how this function is defined in such a way that if you swapped x and y, it would still be the same? Yes? What does that say? Well, that says if I look at the derivative with respect to x versus the derivative with respect to y, it should just be swap x's and y's. So if I look at fxx compared to fyy, if they're the same up to that swap, that's good. If they're not, made a mistake. For xy, I should expect that if I swap, I should not change anything. Let's find out. So by the way, all of that was just mentioned is saying, hey, we've got symmetry here. Let's take advantage of it. All right. Well, let's start. Got to do them all. So we might as well start somewhere. fxx, quotient rule. Low, 1 minus cosine xy, d high. Now, we're taking the derivative with respect to x, so that y is a constant. But we don't want to forget it. Derivative of sine is cosine xy. Derivative of xy with respect to x will be not a y. There's already a y there that it can join, so we get y squared. One of them from the one that's already there, the other one from the chain rule. Subtract. Okay, so we've done the bottom times the root of the top. So we're going to subtract the top, sine of xy times y, times the root of the bottom. Well, the root of the bottom, we've actually done this before. It's going to be sine of xy times y. All right. All of that divided by the bottom term squared. Now, what do we see? Well, you might notice this has a y squared. This has a y and a y, which is also a y squared. That's common. Let's pull it out. So we end up with y squared in the front. And then cosine of xy minus cosine squared of xy. And then here, minus sine squared of xy. All right? All over 1 minus cosine xy squared. Well, what do you see here? Well, we see cosine xy minus 1. Cosine squared, sine squared. Oh, all right. So y squared cosine xy minus 1 over 1 minus cosine xy squared. Well, notice these are almost the same, up to a minus sign. All right, so what can we do? Pull out a minus sign. So we'll pull a minus out, end up with minus y squared, and then we'll have 1 minus cosine xy. All right, that's looking very simple, about as simple as we could hope for. Okay, that's fxx. All right, good. Now, we're going to repeat this for fyy. Okay, now as we do this, spoiler alert, it's going to feel very, very similar. Okay, so fyy, again, quotient rule, we're going to take the bottom times the root of the top, which will be cosine xy. We'll bring out an x by the chain rule. There's already an x there, so that's an x squared. Minus the top sine xy times x times the derivative of the bottom, which is sine xy times x. Now, we again have x squared and x squared and x squared. So that's going to help us. We're going to do the same thing we did before. So 1 minus cosine xy squared. So pull out the x squared, that's in common. And then we have cosine xy minus cosine squared minus sine squared. All over 1 minus cosine xy squared. But cosine squared, sine squared is 1. So this becomes x squared cosine of xy minus 1 over 1 minus cosine xy squared. So I can cancel almost this one upstairs with one downstairs, but it adds a minus sign because the signs are off. So that leaves us with minus x squared over 1 minus cosine xy. All right. Now, you'll notice I've pretty much run out of space. That's okay. I'll grab a piece of paper. And after all, paper is a renewable resource. It grows on trees. Okay, so here we go. So those are our fxx, fyy. Notice I mentioned if you swap the rows of x and y, you go from one to the other. That's a good thing. That should happen because of the symmetry. Okay, now we come to the mixed one. We only have to do it once. And we say, okay, do we do fxy or fyx? And the thing is, we'll get the same answer. So why would we do one versus the other? We would do one. We would prefer one of them if it's very simple. If they're about the same amount of work, it doesn't really matter. All right, so since they look so similar, we'll take fx with respect to y. Quotient rule. So we have the bottom times the root of the top, which is now a product rule. All right, so what is that going to give us? Well, root of the first will be a cosine xy times, because we're taking the derivative with respect to y, and x comes out. So cosine xy times x, then times the second, plus the first, sine of xy, times the root of the second, which is 1. All right, root of the first times the second, plus the first, root of the second. Minus, okay, so low, d high, minus high, sine xy, y, d low. All right, so we're taking the derivative with respect to y. So it would be 0 become positive sine xy, and the derivative of sine x of the xy with respect to y is x. Nice. Good, 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 good. All over the bottom term, minus cosine xy squared. Okay, so we have to simplify as much as possible, unfortunately. So this will take us a minute here. So let's see what we can do. Unfortunately, we don't have that same pull stuff out. So we get a couple things. We'll get cosine xy plus sine of xy. So first, outer, inner, minus xy cosine squared xy. Last, minus cosine xy sine xy. Minus, at least the good news is this will be just one term, xy sine squared xy. All of that divided by 1 minus cosine xy squared. Now, does anything simplify? Oh, it would be nice if that were true. Well, it is, because those terms combine. We have a sine squared and a cosine squared. And so we put them together. Say, all right, well, what would they combine to give us? Well, they would combine and give us cosine xy, xy, and here it's minus xy. All right, so we have this piece here, and then we have plus sine of xy minus cosine of xy, sine of xy, all over, and well, we're running out of space. I'm going to move up here. All over 1 minus cosine xy squared. Phew. Are we done? No. We can keep going, right? Just when you think that you're done, the problem pulls you back in. We can pull out here an xy. That's common. And I'm going to pull out a minus xy. We'll see the reason for that logic in a second. That would leave us with 1 minus cosine xy. Here, they have sine xy in common. I'll pull that out. Sine of xy, 1 minus cosine xy, over 1 minus cosine xy squared. And now, the great aha, pull that out, and we'll go ahead and do that. Minus xy plus sine of xy times 1 minus cosine xy over 1 minus cosine xy squared. Get some cancellation, and we're left with upstairs minus xy plus sine of xy, and downstairs 1 minus cosine xy. And there we go. Our mixed partial derivatives. Whoo! That's a workout. That is a good algebra workout. What a problem. Now, realistically, they won't ask you to do all of these, but they probably pick one. So be ready to answer any of these. But there you go. Life is good. We made it through. Whew. All right. All right. The level surface to the four-dimensional graph for w equals f of xyz equals 3x minus 2y plus 4z over 5x minus 6y minus z at the point 2, 1, negative 3 is a plane. Find a formula for that plane. All right, so what do? Well, it's a level surface. Now, how did we do level curves? Let's think about that. You set the function equal to a number and then figured out what was going on. Same thing with a level surface. Now the question is, what's the right number? So to figure that out, we say, well, look, we have a point, so plug it in. So we're going to plug in f of 2, 1, negative 3. So everywhere where I see an x, I'll put a 2. So we have 3 times 2 minus 2 times 1 plus 4 times negative 3. Downstairs, 5 times 2 minus 6 times 1 minus negative 3. All right, so let's see, we have 6 minus 2 minus 12. Upstairs, 10 minus 6 plus 3 downstairs. All right, well, so far, so like, okay, how do we do anything with this? Well, let's finish it off. And so this is 6 minus 14, that's negative 8. And then 10 minus 6 is 4 plus 3 is 7. All right, so negative 8/7. So this right here is what we would have called height. So the level surface is 3x minus 2y plus 4z over 5x minus 6y minus z, which is the function, equal to the height. negative 8/7. Well, from here, we're hop, skip, and a jump away. Because what can you do? Cross multiply. And, all right, so we have 7 times 3x minus 2y plus 4z equals negative 8, 5x minus 6y minus z. Or 21x minus 14y plus 28z is equal to minus 40x plus 48y plus 8z. Move things across. 21 plus 40 makes 61x. Minus 14, subtract 48 is a number. It's minus 62. So minus 62y. And then 28 subtract 8 is plus 20z equals 0. There's no common divisor of any of these coefficients. It's a plane. We're done. So actually, it looks terrible, but really the key is to say, oh, it's a level surface, so I'm saying my function equal to a value. How do I find the value? Plug the point in to say what's the right value. And then cross multiply, clean it up, life is good. It's nice to have a nice cool down after the problem we just did. Nice. The law of cosines for triangles, c squared is a squared plus b squared minus 2ab cosine c, defines the measure of angle c as an implicit function of the side lengths a, b, and c. On a side note, you can think of law of cosines as a nice generalization of the Pythagorean theorem. And it says, make a note, angle c is opposite of side having length c. Now, the question, find the value of partial c, partial a, when a is root 3, b is 4, and c is root 7. Now, here's the thing. What do we have? Well, we have a relationship, and we're thinking of c is an implicit function for the side lengths a, b, and c. Actually, you can make it an explicit function pretty quickly, but we'll whatever. And so what's the great idea? When we see an implicit function, we say, okay, that tells us, oh, we're thinking of, now in this case, it's c is a function of a, b, c. So we're going to start c squared equals a squared plus b squared minus 2ab cosine c. And we're going to say, well, look, what do we want? We want partial c, partial a. And so we say, okay, so we're taking the derivative with respect to a. So we're going to take that derivative. Now, as we take this derivative, partial a is varying, okay? What about b and c? So the key thing here is we're going to treat b, c as constants. Because we have the three inputs, a, b, and c, and we're asking, well, what happens as we change a? So it's like, well, we're only changing a, treat b and c like constants. So what's the derivative of c squared? 0. What's the derivative of a squared with respect to a? 2a. Derivative of b squared? 0. Derivative of 2ab cosine c. Product rule. You might want to say, well, hey, there's only one a. No, there's two. There's this a, and remember, we're thinking of c as depending on a. Okay, so derivative of the first part with respect to a, 2b cosine c. And then 2ab. Now, what's the derivative of cosine c? Well, the derivative of cosine is negative sine. And then chain rule, derivative of c with respect to a, partial c, partial a, which is what we're after. So now we're like, great. We have all the pieces. So the next thing to do is to figure things out. Say, okay, what's going to happen? We need to plug in. Now, we need to evaluate. So let's talk about what we know. We know A is root 3. We know B is 4. There's no C here. All right, well, whatever. But there is another C. Like, there's no little c. There's a big C. What is that? Ooh, K. We kind of need that, don't we, I guess? All right, so let's come back to our original equation. Let's see if we can figure out what C is. So we know A, B, and little c. So root 7 squared, 7, is equal to A squared, 3, B squared, 16, minus 2 times root 3 times 4 times cosine C. So I'm plugging in our values into here with the goal to find C. All right, so let's see. Oh yeah, let's start moving things around. We can, this is 19, you subtract both sides by 19. 7 subtract 19 would be negative 9. Is that right? No. 7 subtract 16 is negative 9. I also have to subtract the 3. All right. Negative 12 equals minus 2. Well, there's 4 there. Let's go ahead and multiply. So minus 8 root 3 cosine C. So that says cosine of C, well, the negatives go away, is 12 divided by 8 root 3. Now, notice that 12, it actually factors relatively nicely. That's 4 times 3 over 8 times square root of 3. Well, 4 into 8 gives you a half. 3 divided by square root of 3 is root 3. And now we're like, whoa, that's a number we recognize. We've seen this number before. So actually, we know cosine C. And so this turns out to say, oh, that says C is pi over 6. Now, we don't have to actually know that, because notice we really need cosine C and sine C. So if it had been a weird number that we didn't recognize, we could say, well, look, we know cosine C. How can you get sine C? Well, you could say, look, sine squared C plus cosine squared C equals 1. And so sine squared C plus square this, 3/4 equals 1. Sine squared C equals 1 minus 3/4, which is 1/4. All right. Well, that tells us that sine of C is really a half. And it's true. Sine of pi 6 is a half. All right. So C is pi over 6. So cosine of C, root 3 over 2. Sine of C is a half. And it looks like we're almost out of space, but the good news is we're almost out of problem, because we're really very, very close to being done. Very close to being done. We just need to plug everything in. Okay, so we have everything has a 2 in here, so let's go ahead and cancel the 2's. And so we have A square root of 3 minus B, which is 4, cosine of C, square. I said 4, I wrote B. Try that again. A square root of 3 minus B, 4, times cosine C, square root of 3 over 2. And now here, minus minus makes plus, plus A square root of 3, B, 4, and then sine of c, 1/2 times partial c partial a equals 0. All right, so we plugged in a minus b cosine c plus a b sine c partial a. All right, now notice everything has a root 3. So let's go ahead and divide out by a root 3. And so the root 3's go away. So we end up with 1 minus 2 plus 2 partial c partial a equals 0. Well, from here, we're pretty much done, right? 1 minus 2 is negative 1, move it across. 2 partial c partial a equals 1. Partial c partial a equals 1/2. All right, we did it. We survived. Woohoo! Yay us. Yay us indeed. All right, so really the key thing is take your partial derivatives, make sure you know what's constant, plug in what you know, and you can use the original relationship to get your cosine c and sine c. All right, progress. The surface defined by z equals root 9 plus 4x squared plus 3y squared contains the point P is minus 1, 2, 5. Find the unique vector v, AB, so that the function f has 0 change at the point P in the direction of v. All right? V, magnitude, is 2 root 13. Okay? And the first coordinate, A, is positive. All right. Now, let's think about what's going on. So, change, that's secret code. Derivative. All right. There's all these ways to say derivative. Change, that stands for derivative. Direction plus derivative, directional derivative. So what do we want? Well, we want gradient f p dot v, right? This is the directional derivative in the direction of v, is 0. Okay, so that's some information here. All right. So, cool. Now, I want to pause here and say, now technically speaking, normally we say this should be a unit vector. However, because we have 0 over here, we can scale it. So this vector can be arbitrary. We're taking advantage of the 0-ness. All right, so this first bullet point says we need gradient f of p dot v to be 0. All right, with that in mind, let's see what happens here. We have the following. And, all right, so let's talk about gradient of f. So we have our gradient f. It's a function of two variables, fx, fy. So we take the derivative with respect to x. And, well, okay, so if we are going to take this derivative, we rewrite it to be calculus friendly, 9 plus 4x squared plus 3y squared to the 1/2. So the derivative with respect to x, 1/2 times 9 plus 4x squared plus 3y squared to the -1/2 times the derivative of the inside with respect to x, which is 8x. Similar, 1/2, now taking the derivative with respect to y, 9 plus 4x squared plus 3y squared to the -1/2 times the derivative of the inside with respect to y, 6y. So, this gives us 4x, because 1/2 times 8 is 4, over the square root, 9 plus 4x squared plus 3y squared. comma, half times 6 is 3y, divided by square root 9 plus 4x squared plus 3y squared. Okay, so there's our gradient. Where's our point that we plug in? Now, here is sort of a little bit of bad notation in this problem, the way it's written. We really care about these two parts when we talk about the gradient, the x and the y. We really don't want that z part. So we're plugging in -1 and 2. We're going to see 5 show up in just a second. And okay, so gradient f at -1, 2 is, well, 4 times -1 is -4 over the square root of 9 plus 4 times -1 squared, that's 4, and 3 times 2 squared is 12, and comma, 3 times 2, 6, over, again, square root of 9 plus 4 plus 12, and if you look at it, we have square root of 25, which is 5. Coincidence? No, because notice, if you plug in this point into your function, you get this value, which is 5. Okay, so we have -4/5, 6/5. All right, so let's now, with all of this, talk about where we're at. The first bullet point tells us that we need -4/5, 6/5 dot a b to equal 0, or -4/5 a plus 6/5 b has to equal 0. Well, you can multiply through by 5, you can divide by 2, so this says -2a plus 3b equals 0. All right. That's what we conclude from bullet point number 1. Now, bullet point number 2 says, hey, this magnitude has to be large enough. So let's actually do magnitude squared. Get rid of the square root. So we square both sides. Magnitude of e, a squared plus b squared. Here, square that. 4 times 13 is 52. Now notice, 2 equations, 2 unknowns. All right, well, we can solve. For instance, this right here tells us that a is 3/2 b. And, all right, so we can plug in. We get 3/2 b squared. Why did I write 15 here? 4 times 13 is 52. I am so sorry about that. 3/2 squared plus b squared equals 52. Well, that translates 3/2 squared is 9/4 plus 4/4, 13/4 b squared is 52. I can divide both sides by 13, and then I multiply both sides by 4. That tells us b squared equals 16, or b equals plus or minus 2. Okay, so if we have just the first 2 bullet points, we get now that a is 3/2 b and b is plus minus 2, which means at this point in time, we've narrowed it down. If b is plus 2, a is 3/2 times 2, and so that would make it the point 3, 2. Oh, why did I say 2? 4. I was looking at 3, 2. It's not big enough to get that. My apologies. 3/2 times 4 would be 6. So we have either 6, 2, 6, 4, or -6, -4. So that's from the first 2 bullet points. All right. Last bullet point. The coefficient has to be positive for a. All right, done. Sorry, I made some small mistakes over here, but the idea is okay. So the first restriction tells us something about the gradient dot the vector, and that gives us a relationship. The second one says the magnitude, gives us a second relationship, but this time in terms of squares. So you can do some substitution, and you get what it can be up to plus or minus. The third one tells you which one to take. So our final answer is that we should have the vector 6, 4. That satisfies all of these conditions. Good, good. Given that f of xy is g of u of xy, v of xy, use the information in the following table to find the values of f sub x of 2, 3 and f sub y at 2, 3. Now, this problem looks intimidating because there's a lot there. You're like, are we really going to have to use all of that? No. No, 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 no. No. So wait, what's the point of this question? The goal of this question is to say, do you understand what you need? We're going to use a tiny piece of this table. But the question is, what's the right piece for us to use? And what's going on here? All right, so what is going on here? Well, we see we have functions inside of functions. And we're like, oh, okay. So if we have a functions inside of functions, chain rule. Now, the way I start thinking of chain rules, I like to build a tree structure. So I say, all right, my top level, I have G. And it depends on two things, U and V. And now U depends on X and Y, and V depends on X and Y. Okay, great. Well, so where do we go from here? Well, if I want to understand change, I say, well, I look at how does G change with respect to U? That's G sub U. How does G change with respect to V? That's G sub V. U with respect to X, U with respect to Y, V with respect to X, V with respect to Y. Now, these are all partial derivatives. Notice that it's very easy to figure out what the partial derivative should be. What's the top? What's the bottom? So top goes partial V, partial X. Now, here's the fun part. Say, all right, suppose I want to know partial F, partial X. Well, I see two X's. And so I say, well, I'm going to follow my chain down. So F sub X is equal to, follow the road, G sub U, U sub X, plus G sub V, V sub X. And in a similar way, if I want to do the derivative with respect to Y, there's two Y's. So we say, all right, so for the derivative with respect to Y, we have the following. F sub Y is G sub U, U sub Y, plus G sub V, V sub Y. All right, so this is telling us what to look up. One more thing we need to figure out is what are the values of the variables. Now we see X and Y, so we say, X should be 2, Y should be 3. Okay, that's not so surprising. What about U and V? Because we need to understand that. Well, to figure out U, we say, well, U, that's going to be U at 2 comma 3, because U depends on X and Y. We know X and Y. So we look to our table. So U at 2 comma 3 is 3. All right, good to know that. And V, which we plug in X equals 2, Y equals 3. So we say, okay, V at 2 comma 3 is minus 2. All right, so we've done the first part of our table. Has helped us to figure out, oh, we know the values for u and v. Okay, so here we go. We've got a lot of work done already. And I know you're thinking, like, you've hardly done anything. We've done the hard part. We've gotten the concept down. We figured out chain rule. We got our structure. We have our generic formulas. We figured out u's and v's. So here we go. So what does this say? It'll be f sub x at 2, 3 is g sub u. But now, notice what g is. G is a function of uv. So we don't plug in the xy, we plug in the uv. So g sub u at 3, negative 2, u sub x, u is a function of x and y, so you plug in the xy, 2, 3, plus g sub v, again, g is a function of uv, 3, negative 2, and uv sub x, and v is a function of x and y, so it's v sub x at 2, 3. All right, so what data are we trying to get from our table here? Well, you want g sub u at 3, negative 2. So that's here, 4. Okay, so this is 4. U sub x at 2, 3. 4 plus g sub v at 3, negative 2. That's negative 3. And v sub x at 2, 3. And that's 2. So we get 16 minus 6 is 10. All right, we're halfway done. Now we'll repeat, but for our other variable. Okay, so we have f sub y at 2, 3 is g sub u, but g depends on u, so we use our variables. So 3, negative 2, u sub y, and u is a function of x and y, so we use our x and y values, 2, 3. G sub v, again, back to our u, v values, 3, negative 2. V sub y at 2, 3 equals. All right, so what do we get? Well, g sub u at 3, negative 2. That's 4 again. U sub y at 2, 3. That's 3. Plus g sub v at 3, negative 2. That's still negative 3. And then we're going to have our v sub y at 2, 3, which is over here, which is 1. So we get 12 minus 3. 12 minus 3 is 9. We're done. Notice we didn't touch anything here or here or here or that. There's a lot of stuff we didn't touch. And that's the point of this problem. This problem is testing you on, do you know what information you need? And can you extract it? And so it looks very like, but when you realize, oh, I understand the chain rule, I know how to find my u and v, and I plug everything in, it's not so bad. A little bit of practice, and then it starts to be not just not so bad. It says, oh, I can do these problems because you can do these problems. You're great. You're awesome. Let f of x, y, z be a smooth function of 3 variables. Let g of uv be f of u cubed, u plus v squared, uv. Let P be the point 1, 5, 2. All right, we've let a lot of things be true. Okay, are we going to do anything? Given that the gradient of f at the point P is 3 minus 1, 2, find g sub u of 1, 2. All right. Now, your first reaction might be like, what? What's going on here? Well, we can kind of see the clues here. Notice, what do you see here? Those look like functions of u and v inside of a function, f. Functions in function. Chain rule. All right, so this is a chain rule problem. Okay, but how do we figure out what's going on? Well, we see we have the following. We really have f, which is a function of x, y, and z. And then x, well, that depends on u. Y depends on u and v. And z depends on u and v. All right, so we have this nice chain here. All right, and okay, well, what do we want? We want to find g sub u. And we say, well, hey, there's 3 u's, so we're going to have a lot of work to do ahead of us. And all right, well, so just applying the chain rule formula, we get the following. G sub u is, and let's label these sides, fx, x sub u, fy, y sub u, y sub v, fz, z sub u, z sub v. So is f sub x, x sub u, plus f sub y, y sub u, plus f at z, z sub u. Now, we want it at a particular point. So, we're going to work on unraveling things. We need to find out what's going on. So, okay, so we want g sub u at 1, 2. So that says u equals 1, v equals 2. We're going to do a little bit of side work here. We have x equals u cubed, y equals u plus v squared, z equals u times v. So when you plug in 1, 2, what does that correspond to? Well, that says x would be 1 cubed, which is 1. Y would be 1 plus 2 squared, so y will be 5. And z will be 1 times 2, which is 2. 1, 5, 2. Have we seen that before? Yeah, right there. Like, oh, is it coincidence? No, because we're going to need it. Okay, how do we use this part? Ah, good question. Okay, so what does this tell us? Well, remember, these are partial derivatives. So gradient f at P is f sub x at our point P, 1, 5, 2. F sub y at our point, 1, 5, 2. F sub z at our point, 1, 5, 2. And we're told we get 3 minus 1, 2. So we say, oh. So what this is telling us is f sub x at 1, 5, 2 is 3. F sub y is minus 1. And f sub z is 2. All right. So let's put it all in. So we're going to get g sub u at 1, 2 is f sub x at P. Well, all right. Fx at 1, 5, 2. X sub u. Well, we didn't write that down. Let's write that down. X sub u, 3u squared. Y sub u, 1. Z sub u, v. Plug it in. We're at u equals 1, v equals 2. 3, 1, 2. All right, so we're going to have fx at 152. Then we're going to have x sub u, and I'm going to first off write it all out, and then we'll plug in these numbers. X sub u at 1, 2, plus f sub y, 1, 5, 2, x sub u, 1, 2, and f z, 1, 5, 2, and z sub u, 1, 2. Okay. Now we just read things off. F sub x, 3. X sub u, 3. F sub y, minus 1. Y sub u, plus 1. F sub z, 2. Z sub u, 2. So we get 9 minus 1 plus 4. And, all right, well, that sounds like 12. And we're done, because we found what we wanted. So it's another chain rule, and the key to recognize is giving you this gradient is giving you the values you need in this chain rule. And then, of course, for these other values, since you have explicit functions, you can explicitly find the derivatives and plug in and get those values. So this is wonderful. We got everything that we needed. Yay, us. Good job, us. Woo! Let f of uv be a smooth function such that f sub u at 2, 2 is 2, f sub v at 2, 2 is 5, and let g of x, y, z equal f of x, y, comma, y, z. Let w be the unit vector in the direction in which g of x, y increases the fastest at x, y, z equals 2, 1, 2. Find the rate of change of g at the point 2, 1, 2 in the direction of w. All right, good. Lots going on here. So, what do we have? Well, notice that really we have f depends on two variables, u and v, and then u and v depend on what? X and y and z. So, we get the following. F depends on u, v, and then u, well, it really depends on x and y and z. Okay, so we have that information. Now, what do we need to do? Well, we're talking about direction, because it says direction, and we also have words like rate of change, which means derivative. So it's a directional derivative for g. So we need to do the gradient. So directional derivatives are built off of gradients. All right, so here we go. Here we go. We have that, what is the gradient of g? Gradient of g will look like g sub x, g sub y, g sub z. Now, can we figure these values out? Well, if we come over here to our diagram, we can say, well, yeah, we can figure these out. And in particular, we can say, look, we have f sub u, f sub v, and then we have u sub x, u sub y, v sub y, v sub z. But more explicitly, we really can say, look, u of xy is x times y. So u sub x is y, and u sub y is x. V of yz is y times z. So v sub y is z, and v sub z is y. So we say, all right, we've got all this lovely information. Let's use this to update that. So say, all right, well, let's see what we have here. So I'm taking g with respect to x, that'll be f sub u times u sub x, right? And that's the only place where an x shows up, comma. G with respect to y, well, shows up in two places, f sub u, u sub y, and then there'll be an f sub v, v sub y. And then for z, there's only one, f sub v, v sub z. Now, that's just generic. Let's get to the point, our point, the point we care about. So, we care about u and v, well, we claim is 2, 2, but we also have x, y, z is 2, 1, 2. So the gradient of g at 2, 1, 2, well, notice if we have that x equals 2, y equals 1, z equals 2, then u is 2 times 1, and v is 1 times 2. So we are at 2, 2. So that will be f sub u, 2, 2. And then we have u sub x. U sub x is y. Y is 1. Comma. F sub u at 2, 2. U sub y. U sub y is x. X is 2. So times 2 plus f sub v at 2, 2 times v sub y. V sub y is z, and z is 2, comma, f v at 2, 2, v sub z is y, and y is 1. But we know these values. So f sub u is 2, so we get 2 times 1, which is 2. Then we have 2 times 2, which is 4. And here we have 5 times 2, which is 10. So you have 4 plus 10, 14. Then we have f sub v at 2, 2, which is 5. So 2, 14, 5. All right, so there's our gradient of g. That's the hard part. Now, the rest of it says, look, we need to find the rate of change of g at the point 2, 1, 2 in the direction of w. Do we need to find w? No. The problem doesn't ask us to find w. So you're like, wait, what? How can we answer this question without finding w? Steve, you punk, you got to know w, right? No. Okay, so check this out. Check this out. We're going to do something. Now, suppose we have our gradient of g at our point, and we dot it with the unit vector w. What's true? Well, you're saying, well, I don't know what w is. That's great. I don't want you to know. I just want what's true. If I take the dot product of two things, what can we say about the dot product of two things? Well, it's the magnitude times cosine of the angle, right? Well, yeah, that's just the dot product. So magnitude of gradient of g of p, magnitude of w, cosine theta. But what is w? W is a unit vector. So what's the magnitude of a unit vector? 1. So this directional derivative turns out to be the magnitude of the gradient times this cosine theta. Now you're like, oh, well, the gradient is fixed. The only thing I can change is cosine theta. And now, what's true about cosine? It's between -1 and +1. And we can achieve -1. We can achieve +1. So we say, oh, well, the biggest this can be is the magnitude of the gradient. So the big aha to say, look, if I want to get the largest possible directional derivative at a point, the greatest rate of change in the direction where it's going the fastest, it's the magnitude of the gradient. So, we're almost done. The last thing for us to do is to take the magnitude. Now, you might say, have we talked about this? We will. This problem gets a little bit ahead, just a little bit. We're about to talk about this. So, but I promise you, we will talk about it. All right, so that's the square root of 2 squared plus 14 squared plus 5 squared. Well, 2 squared is 4. 14 squared is, say it all together, 196. Good, 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 good. I'm glad we got it all together. 5 squared, 25. 4 plus 196 is 200. 200 plus 25 is 225. Well, is that a square number? It is. This is 15 squared, which means our final answer is 15. All right, so what's the outline for this problem? It's a chain rule problem. Use the chain rule and the information we're provided to find your gradient. And because we're trying to find maximal rate of change, that's this going out of its way to say the phrase maximal rate of change, you find the magnitude of the gradient. And that's your answer. And, we made it. We made it. Thank you for being so patient. And I know this was a long one. Not this particular problem. There's a lot that went on in this quiz. And I'm glad you're working at this. Keep working at this. You are wonderful. You can do this. You can learn these things. You are capable. You are a strong, beautiful mathematician. Be the best you can be. And I hope to see you again. Bye.